How can fossils help us understand how the oceans changed over time? Fiona Anstey is a graduate student at MIT studying geology. She examines ancient life preserved in rocks to look for chemical clues about temperature hundreds of millions of years into Earth's past.
Hello, everyone. My name is Fiona, and I'm super excited to talk to you guys today about how I explore ancient oceans through my research here at MIT. But before we get into that, I think it would be a good idea if I introduce myself and tell you a bit about who I am. So, as I said, my name is Fiona, and I'm half Spanish from the beautiful region of northern Spain called Galicia, and I'm half American. I was actually born in the capital city of the United States, Washington, D.C., which you can see here on the map in the star furthest to the left. But I also lived in London for 4 years, which is the star in the middle of the map. But I spent most of my childhood growing up in Tokyo, Japan, which is all the way on the right of the map, that star all the way over there. So I grew up speaking some Spanish, English, a bit of Japanese, and I even learned French in school, so kind of a mix of things. But one thing about me is that I always loved hiking and spending time outdoors. Here's a picture of me with my dad in the mountains. He used to take me hiking before I could even walk. He would just carry me around in his backpack. But in school, I carried this interest with me. So at the British School in Tokyo, I took 4 different A levels. I took English, maths, Spanish, and geography. And I love geography because there was a human component where we learned about how the human world works and immigration, and a physical geography component where we learned about how the natural world works. And then I went back to the US for university at Amherst College. And what was amazing to me about Amherst was that it had an open curriculum, which meant every semester I could take whatever classes I wanted to. I got to take philosophy and art history, but I ended up doing a double major in math and geology. I also got to work at the Natural History Museum on campus for all 4 years, which was very fun. And that leads me to where I am now at the Department of Earth, Atmospheric, and Planetary Sciences here at MIT, where I get to study geology every day. But wait, what is geology? Geology is the study of our planet. And geology seeks to answer fundamental questions about the way that the Earth works. So these are questions like, how old is the Earth? Why did the dinosaurs go extinct? How and when did life on Earth begin? What causes earthquakes? And a question that really interests me, which is how has climate changed in the past and how will it change in the future? Well, it turns out the Earth is very old. It's around 4.5 billion years old. And that is a really big number. That's a lot of zeros. So to wrap our heads around what this really means, we can think about the history of the entire Earth as one calendar year. Okay, so let's imagine that the start of Earth history was the beginning of the year on January 1st. And the modern day, the time that you and I are living right now, is New Year's Eve on December 31st. So in this framework, then the first life on Earth doesn't appear until the end of February. And the first life on Earth was very small and very microbial and not that recognizable. We don't get things that look very recognizable until much later. So like the first insects would appear on December 1st. Dinosaurs don't come up until December 13th. But what about humans? Well, humans don't appear until 2 minutes before midnight on December 31st. And actually, all of recorded human history would only be the last 82 seconds. So this gives us some perspective on how long the Earth has been around and how little of it we've experienced as humans. So a brief recap of the history of life on Earth. Life began very small. So small, in fact, that it was microscopic, mostly microbes and little bacteria. And over time, life evolved and became more complex. And then we had, about 500 million years ago, a very special time in geologic history called the Cambrian period. And during this time, most of modern animals that we experience today their first appearance in the fossil record comes at this time. So it was very special. And over time, things evolved further. We get insects, plants, and dinosaurs. There were extinctions, things came and went, and eventually humans. But the reason why we know about this at all is because we have an ancient record of life on Earth through fossils. This is a rock that I took a picture of in the lab just 2 days ago of some 500 million-year-old shell fossils. And I'd actually like to show you another fossil that I have right here, which is a leaf fossil. So the kinds of rocks, so fossils are traces of living things that are preserved in rocks. And the kinds of rocks that preserve these fossils are called sedimentary rocks. We get several different kinds of sedimentary rocks, like sandstones, which form from ancient sand, limestones, which form from ancient bits of shells in the ocean, and mudstones, which, you guessed it, form from ancient mud. And this particular mudstone on the right is very special. It's actually from the Natural History Museum at my university, Amherst College. And if you look closely, you might be able to see that there are dinosaur footprints left in this mudstone. So you can see that there's a record of life preserved in these rocks. And what makes sedimentary rocks particularly special is that it allows you to see millions of years into the past. And the way that we do this as geologists is using a special concept called stratigraphy. And that's a pretty big word. You guys don't have to remember it, but here's what it means. So imagine that this line here is the surface of the Earth. That's the ground. Over time, we'll get little particles that accumulate on the surface. So for example, we might get some sand if we're like in a beach environment, for example. And maybe over time, we get some sea level rise, and then some shells in the ocean fall down to the bottom, and we get some shells accumulating. Maybe the environment changes again over a few million years, and we get some mud, maybe some shells again. And so you can see what happens is this different material gets stacked on top of each other in layers. And over time, those layers squish and harden and compact, and they turn into rock. So the sand turns into sandstone, and the shells into limestone, the mud into mudstone, and we get this record of rock. And we know that looking at these different layers, the layers on the bottom were accumulated first, and the layers on the top accumulated most recently. And that tells us that the stuff on the bottom is the oldest and the stuff on top is the youngest. And so in that way, you can look at these rocks and you know something about the environment in which they formed at that time. Like when we look at that limestone, we know that at one point it was underwater in the ocean. But what about my research? So I'm studying sedimentary rocks that formed in the ocean 500 million years ago during that Cambrian period that we talked about. So in our calendar analogy, that would be around mid to late November. Now, the Earth during the Cambrian period looked pretty different. So on the left, we have the map of what the Earth looked like back during the Cambrian. And on the right is the Earth today. And you can see that the continents are all in different places. In fact, this yellow star that you see is the location of London. So not only was London in a totally different place during this time, but it was also underwater in the ocean. But life was also very different during the Cambrian. Like we were saying, life originated in the ocean, and during the Cambrian, the fossil records suggest that life was exploding, and we got for the first time, many new different groups of animals that were evolving. And we had things like, for example, on the right, this is called a trilobite. This is a fossilized trilobite, which is a creature that lived on the bottom of the ocean. And it's a relative of horseshoe crab, if you've ever seen one of those on the beach. But I'm interested in what the climate was like at this time, and more specifically, what the temperature was in the ocean, because all of this life was biodiversifying in the ocean, and temperature is very important for biology. If it's too hot, biology struggles, and if it's too cold, biology struggles. So it's important to understand what the temperature was at this time. But unfortunately, we can't just travel back in time 500 million years and stick a thermometer in the ocean. That would be nice, but we can't do that. So instead, we use fossils. In particular, we use fossil shells. And that's because shell building creatures build these structures out of chemicals that are around them in the water. And the way they do that, the organization of those chemicals in their shells is temperature dependent. And what that means is that the organization of those chemicals is different if it's hot or cold. And that is something that we can measure. So we have these fancy instruments here in the Bergman lab, which is where I work, and we can measure those the organization of those chemicals and interpret what the temperature was like all the way back during the Cambrian period. So in order to collect some shells from that are 500 million years old, I went to the Museum of Natural History at the University of Oxford. I took a plane and I traveled all the way from Boston to London, and I took a 2-hour bus and I arrived in rainy Oxford. Here's a selfie I took in front of the museum. And before I tell you a bit about my samples, I'd just like to take a moment to talk about how special this museum is. The building itself is actually the first science building on Oxford's campus. And if you ever go, you should take a look up above you, because these iron beams on the ceiling are built to teach you about the local plants in the UK. And all the iron is like different flowers and leaves and trees from around the UK. And the different columns are all made of rocks from all across the UK. So the building itself, the architecture, is also teaching us about the natural world around us in the UK. And of course, the collections are amazing. So what about my samples? Well, I collected what are called small shelly fossils, and they're all from this time period. And what's really amazing about getting to collect samples at a museum is that you're in one place, but you can sample the world. I was able to sample material all the way from Siberia to the US to Australia. And one thing that is also really cool is that a lot of this material is already separated. Because you may be wondering, in the middle here, I'm looking at something under a microscope. That's a fossil. It's not in the rock. So the way we do this is actually you can get the fossils out of the rock, because these fossils are made of a different material. It's a mineral called apatite. And so we actually dissolve the rock, and all the insoluble material that's in the rock gets left behind. And that's what I'm looking at here under the microscope. And you may be wondering, well, this doesn't really look like a shell I see on the beach. And that's because this actually belonged to a creature that looked something like the artist rendition that you see on the right. And those are kind of horny shell material that existed kind of on their shoulders, let's say. And it's also interesting that this shell formation was happening during this time because we got predators for the first time. So these creatures had to protect themselves with features like these horns. So those are my samples. But what am I doing next? Well, This graph is showing each circle is a different temperature measurement from different fossil materials over time. So the modern day is on the right, 0 million years ago, and the Cambrian period is all the way on the left, 500 million years ago. So uh, dots that are towards the top of the graph are cold temperatures, and dots towards the bottom are hot. And you can see that during the Cambrian, it was very hot, according to the measurements that we have today. But I'm using a different technique from the traditional chemical measurements of ancient temperatures. And so I'm really excited to be making some new measurements this semester that I can add to this temperature record. So thank you very much for listening, and I'm very excited to take your questions. And if you'd like to keep following my work, feel free to follow my Instagram account, Fiona in the Field. Thank you.
Wonderful. Thank you so much, Fiona. That was spectacular. And we have some amazing questions in the Q&A pod from the Nord Anglia students today to get us started. And so the first question we have is from Ashray. And Ashray is wondering, how long does it take for fossils to get preserved? How long does it take before we have fossils contained in rocks?
Yeah, that is an excellent question. Fossils, the process of fossilization takes millions of years, and it's actually a pretty rare occurrence because you can imagine that when an animal dies, for example, its remains are left behind, but there are many things that can disrupt it and break it into pieces over millions of years. And so the fact that we get some of these remains preserved in the rock records is actually very special. But keep your eye out. If you're ever on a hike, you might find one.
I certainly will. And a follow-up question from Nina now. And Nina's wondering, how do you know how old the fossil was? How do you know how old those rocks are that the fossils are in?
That is a fantastic question. And it depends. So, for example, in the layers of rock that I showed earlier, you can get kind of comparative age, you know, that something is older or younger. But if you want an exact age, there's a lot of different techniques that you can use. One of these is it's called radiometric dating, which basically you get to use these radioactive elements that you can find in rock, and the way that they decay is predictable. And so you can measure how much of the parent or the daughter you have, and that will tell you how long it's been decaying, which will tell you how old the rock is. But actually, fossils are a great way to date rocks because we have this record of ancient life. And so if you see a certain kind of creature fossilized in the rock, you know, okay, well, that creature lived around this time. So that means that this rock had to be deposited at that time. So fossils are also a way that you can date rocks.
That is super, super cool. Now we have another question about finding these fossils by Saiba. And Saiba's saying, we are learning about erosion in class right now. And so how does this link in with finding fossils? And does it help us find fossils in the ocean?
Wow. Okay, I have a lot of thoughts on this. So erosion is really interesting because we can think about erosion at different times, right? Like you can think about erosion early on in the history of that rock, because sometimes we get in the rock record a period of missing time. That's called an unconformity. And that can happen when we get rocks exposed at the surface and there's a lot of erosion that breaks it up and takes it away, and then new materials deposited on top. But because that chunk was taken out, we get a kind of lost time in the rock record. And so in that way, it's not great for preserving things because, you know, it destroys part of the record. But in other ways, it can be very helpful because, as you can imagine, when we have this deposition of rocks in layers, why would we see the rocks underneath? Why would we may only see the rocks that are most recently deposited? The reason why we see those ancient rocks is because sometimes they're uplifted in mountains and eroded, and so we get to see the older rocks exposed. So erosion can be both helpful and detrimental, but it's certainly a very important process.
And Fiona, just to follow up to that, can you quickly walk us through this idea of erosion? What is it? What is actually happening? What does that mean for those of us who are not as familiar yet with geology?
Yes. Okay. So erosion is a concept in geology, which is basically where you get the breakdown of rock and transport of the broken down material away. And you can get the breakdown through rain. Water is a great medium through which rock can be broken up. In rivers, in the ocean, you can imagine like wave action going on a cliff, for example, that will break things up, or like little particles in a river. As they get travel down, they become smaller and smaller. Also wind can erode things. You can also get chemical processes like acid rain, which is basically where carbon dioxide in the air dissolves into the rainwater, and so you get slightly acidic rain. So if you ever walk around like ancient like stone statues, sometimes they are kind of discolored, and that can be because of the chemical processes of acid rain.
Got it. Thank you for walking us through that. We have a few more fossil questions from really excited future geologists here. So Arav is wondering, what tools do you use to break down these fossils from the rock? How do you break them into pieces? How do you get them out of the rocks so that you can analyze them?
Yes. Well, we use a couple things. So when we're in the field, well, I was in a museum, but sometimes we do actually go out into the mountains, and we use a rock hammer, which I wish I had with me, but it's about this big, can be bigger. And we basically like smash the side of the mountain, get a pretty decent sized chunk for what we're looking for. And then for these small shelly fossils, like I said, because they're made of a more insoluble material, apatite, which is phosphatic, then we can put it in a weak acid like acetic acid. And over time, the rock will dissolve and you'll get like those little particles left behind, that we can then look at under the microscope.
Wow, got it. And Prahan is wondering, and you mentioned your time at the museum, but how do you keep the fossils and these artifacts of past life so safe?
Yeah, well, I was actually very lucky because in order to do these chemical analyses of the fossils that I have, I actually have to destroy them. I have to crush them into powders before I put them into our instrument. And the people at the Natural History Museum were very kind, and they let me take the samples back to the US to do this process. I had to sign a lot of official documents, but it's very exciting, and I feel very lucky that I get to analyze them.
It must be really, really cool to be working directly with ancient life that is 500 million years old in that way. That is such a huge privilege. We have a question from Rayansh now, given your experience with fossils. And Rayansh is wondering, what is the strangest or weirdest fossil you've encountered so far in your research?
Wow, what a good question. The strangest. Well, okay. Okay, it's actually one of my favorites. But there is a fossil called a stromatolite, which is actually a type of algae. So it's kind of like a sticky microbial mat that was really important in the geologic history, because it was one of the first photosynthesizers. So it was really important in oxygenating the ancient atmosphere. through photosynthesis. But it looks kind of weird. And maybe if you didn't know if it was a fossil, you might not think it was a fossil because it kind of just looks like some crinkly layers in the rock. It's really cool. I have a piece that I polished that's very beautiful. But yeah, maybe that one.
I think that would probably be one of my favorite fossils too, Fiona. It's really cool to see how cyanobacteria and these microbes over time uh, are preserved in a very weird lasagna-like structure and
Right.
how important they are to us being here today and for making the oxygen that we breathe. And now we have a follow-up question from Ashray. Speaking of favorite fossils, Ashray says that the leaf fossil you showed us is beautiful, and I agree. What are some of the other fossils that you've come across while studying fossils from the Cambrian?
Yes, well, a lot of them are because it's so far back in time. Like for example, these small shelly fossils, a lot of them look kind of just like little bits and pieces of like shells or those like shoulder horns. We also do have though those trilobites, which are really cool. Those relatives of the horseshoe crab. And you also get some brachiopod fossils. Brachiopods are kind of like those shells that you see on the beach today. I showed a picture of them, but yeah, so it's all marine creatures, but certainly some things that look quite different from what we have in the modern period.
Got it. And now, Roshun is wondering, how can we tell the temperature? So you mentioned you're studying these ancient ocean temperatures using these fossils, and that's a new way to examine those temperature records. How can we know what the temperature was from that? What do you do in the lab?
Yes. Okay, this is a great question. So what we do is we're looking at, so traditionally the way you measure temperature that is giving us these really hot temperatures that don't really make a lot of sense given the biological history, is you measure the ratio in the molecules of mm, well, I'll start with this. We have different elements like carbon or oxygen, and different elements can have different masses. So you can have a heavy carbon or a light carbon, heavy oxygen, light oxygen. These are all different versions of the same elements. And you can measure the ratio of heavy to light elements of oxygen in the shells because they're made of a molecule called calcium carbonate, which contains oxygen and calcium and carbon. And when you measure this ratio, it can tell you something about the temperature of the water from which that molecule was formed, because the molecule is formed out of those chemicals that are in the surrounding water. But there's a lot of issues with that, including that you have to know something about the ratio of those heavy to light oxygens in the water, but we don't really know that. And going so back far in time, we just kind of assume it's the same as today, but there's a lot of issues with that. And so the technique that I'm using doesn't measure the ratio of those heavy to light elements of oxygen. Instead, we look at the likelihood of heavy elements to bond with each other. So, for example, in the calcium carbonate molecule, the likelihood of heavy oxygen to bond with a heavy carbon compared with like a random distribution. And that is dependent on temperature and not dependent on the ratio of those heavy to light elements in the surrounding water. And so because of that, it presents an opportunity to measure temperatures that are potentially more accurate.
Got it. So to kind of sum that up, there are really interesting chemical signals in these rocks, and you're looking at these chemical signals in a little bit of a different way than folks have previously to pull it out. And it sounds like you're doing a lot of chemistry in the lab as well. Tell me how geology and chemistry are linked, and are there other disciplines that geology intersects with?
Absolutely. I love this question because the way I view geology, and actually in one of my geology classes, I was asked to draw a Venn diagram of different circles. Where does geology fit in with math and chemistry and physics and biology? And in my view, it's in the middle of all of them because we need to use chemistry because we're looking at the chemistry of these oceans, of these shells. We need to use physics. What were the dynamics of the ocean at this time? How did currents influence things? We also need to use math, which is the language of chemistry even. And so one thing I really like about geology is that you kind of, I always really enjoyed a lot of different subjects in school. And so it kind of allows me to explore our Earth using lots of different tools. And so I view geology as a science that is applied to the Earth. So if you are interested in chemistry, you can be a geologist, or if you're a mathematician, you can be a geologist, or a physicist, or a biologist. If you love nature and if you love the Earth, then you probably already are a geologist.
That is fantastic, and I agree. Geology is for everyone. And now, before I move on to asking some questions about your background and how you got to studying geology, we have a fantastic question from Rayanch who's wondering, how do marine fossils help us understand climate change or how the ocean's chemistry changed over time?
Yeah, that's a great question. And kind of the way I think about it is these marine fossils, they lived in the ocean, they formed in the ocean, their shells were created out of the chemicals in the ocean. And so they're kind of preserving the conditions which they formed in the same way that the rocks preserve the environment. So, like we talked about, the sandstone, you can see maybe it was a beach environment. The mud, we know it was wet. So basically, it preserves these chemical clues in the record of where they formed.
Got it. And now moving on to your story and the history of Fiona. Isabel is wondering, what was your favorite subject in high school and which one helps you the most now?
Ooh, good question. I'm very bad at picking favorites. But I did really love actually my English classes. I took A-level English and I got to read Shakespeare. I loved Hamlet and poetry. I actually thought I would be an English major. But I was still able to take a lot of English classes in college. And I think that it's really enriching to have a lot of different interests and hobbies. And so I would recommend not letting go of those, even if maybe like geology and English literature don't seem super connected. I use my writing skills every day. And so things will help you in ways that you don't expect. But probably the class that was most useful to me was geography, for sure, because I got to learn about like river systems and how erosion works, for example, very early on in my career. And so when I came to university, I already kind of had an idea of some basic geology concepts, and that was really helpful for me.
That's fantastic. And as a nice segue to our next question, Nishka is asking, you mentioned that you grew up and spent many years in Tokyo. Did any of the city's geographical features help foster your love for the natural world and geology?
Wow. Well, unfortunately, there's not a lot of nature in Tokyo as a city. It's very urban. Although now that I say that, I disagree. Because Well, I do think the fauna, the plants in Tokyo are just absolutely beautiful. I used to live on this street that had cherry blossom trees in the middle of the street, and it was so beautiful. And in the springtime, they would just explode in pink. And I remember it was beautiful when it was on the trees, but it was also beautiful when the blossoms would fall onto the ground and you get like a carpet of pink, which was very amazing. So I think that was very nice about the city. But Japan as a country is very mountainous, and public transport is amazing. And so we would just take the train and go hiking sometimes on the weekends. So I think for sure that definitely fostered my love of rocks and nature while I was there.
That is wonderful, and I really hope that all of us can visit one day to
Yeah.
see that beautiful carpet of cherry blossoms that you observed. We have a question from Nina now, who's wondering who was your favorite teacher throughout, school or perhaps even college?
Wow. Well, I hope no one gets mad watching this. Um, hmm. I think I was really lucky. I had a lot of excellent teachers. Um, but one of my favorites was actually a math teacher that I had at Amherst College who really helped me to feel confident about myself as a scientist and as an academic and someone who loves learning. I remember one time I really bombed my first exam. I did really badly and I was feeling stressed, and I came to his office and he took out his exam from when he was my age. And it was like not a very good score. And he said, Fiona, if I was able to get through it, you can also get through it. And that for me was a really special moment. And I think that it reminded me that failure is normal and that it's not actually a bad thing. And that, yeah, it's not always a clean, perfect road forward. Uh, so that was a really, I think, important moment for me. But I've had a lot of good teachers.
Wonderful. And we have quite a few students who are curious in the chat about your favorite book. And if you have any books you'd like to recommend, we have students asking, perhaps you could tell us your favorite geology book. And we have students asking about your favorite English book, since you mentioned you really enjoy studying English.
Wow. Okay, as I said, I'm very bad at picking favorites. So you guys are asking me some hard questions. But my favorite geology book is called Timefulness. And I'd really recommend you read it. It's written very well, and it's fantastic. It will take you through so much of Earth history. It's just an adventure book, but about the Earth. And about the first geologists and how things were discovered. It's a fantastic book. Okay, so Timefulness. And then my favorite like novel. Oh, very good question. Well, as a kid, I always loved Dracula by Bram Stoker. It's a very good book, very exciting book. Um, but I also really recently, well, in the past like 3 or 4 years, I read A Tale of Two Cities, which is about the French Revolution. And I just thought some of the descriptions in that book were just, they transport you. And so that's also another one of my favorites. But Timefulness and Dracula and Tale of Two Cities. That's my answer.
Okay, really good answer. And so we have so many amazing, amazing questions in the Q&A pod, but we only have time for one more. So to wrap us up, Isabel is wondering, has partaking in this type of research about our ancient world changed your view on how you see things in the natural world? And if so, how?
Oh, I love this question. Absolutely. And actually, even in my early geology classes, I remember learning about glaciers and the features that these rivers of ice, glaciers, leave behind on the Earth's surface. And then I look back at some pictures that from a family trip to Glacier National Park here in the US in Montana. And I saw the features that we were talking about in class in the textbook, and I was so amazed. I thought it was so cool. And I really do think geology, learning about geology, changes the way you see things, and you will see the same places with new eyes, and you'll see new places with new eyes. And it's really a really cool way to experience the Earth, I think, knowing about how things were formed so long ago.
That is so wonderful and beautiful. And it's amazing to know how science can really change the way we see things around us. Now, before we go today, I wanted to let everyone know I hope that you'll join us for exciting coming abstracts later on this fall. And to end, I'd like to thank you all for joining us today. Thank you to all the students for asking such fantastic questions. I really think we have future paleontologists, geologists, marine biologists in with us today. And I'd like to thank the MIT Nord Anglia Education Collaboration for making this wonderful series possible. Thank you again very much, Fiona, for sharing your research and exciting story with us. I'm really excited to follow your coming scientific career. Thank you.
Thank you.
Okay, goodbye, everyone. See you all next time.